In my town, in the north of Italy, which is very close to Swiss border, very close to the Alps, the first hydropower plant had been built there. My town, which is small, has been the first town in Italy to have electrical public lighting. There, the first car in Italy has been built. My father told me about those stories, and what I learned from that is really that there are no limits. You can make a revolution from a small town.
Welcome to the world-changing podcast.
Was that too much? Yeah, that was probably too much. But let's keep it. We'll keep it anyway. How about this? If we do the podcast and the world doesn't change, then we can take that out. Welcome to the World-Changing Podcast, where we deconstruct the projects and products that are moving us towards a decentralized and carbon-free future. We'll talk to the skeptics, supporters, and innovators in the fields that depend on electricity to run their industries, which is changing every single day. I'm your host, Greg Robinson, co-founder of Aston Labs, a decentralized infrastructure company. And on the other side of the camera here, we have Flo Lumsden, our producer, and she will make sure that the train stays on the tracks while we do this.
Good morning,
Morning.
Greg. I'm excited to recap our conversation with Claudio from Energy Dome.
It was awesome.
It was so awesome. I learned so much. He did a great job of explaining how the Energy Dome works, and I find it really cool. It's like a brand new invention. Power creation, power storage, and deployment. It's super sustainable. What were your big takeaways?
Yeah, so when I first met Claudio, I was telling him about at Aston, we're working to deploy clean energy campuses. And the biggest question I always get is, how are you going to make clean energy work around the clock? And so I was at COP 28, standing in this giant museum, and I met Claudio and I told him what we were doing. And he said, we've developed this company called Energy Dome, and we're focused on basically making clean energy, namely solar and wind, work around the clock. And so, that's a huge missing piece is how do we get energy storage for 12 hours, 10 to 12 hours? That's what we need. And so, that's the major takeaway for me. But even beyond that, just like Claudio's background, his history as an engineer, it's very rare to find somebody who can be like that deeply steeped in the engineering and then also several times build businesses that have such a huge impact. So let me do the formal description. So Claudio has a master's degree from Polytechnic University of Milan, mechanical engineering. He specialized in turbo machinery, energy production, and conversion. He was also awarded the Cassini Award and has filed 45 patents. He's the founder and CEO of Energy Dome, which we go into at length during the episode, so I won't spend too much time on that. Claudio has founded multiple successful technology ventures in the energy sector, taking them from initial concepts to market leadership. Prior to Energy Dome, Claudio founded and led Exergy, which developed and installed more than 500 megawatts of binary cycle geothermal plants. And the critical element, going back to what I was saying before, of Exergy's success is the radial outflow turbine, which was patented and developed by Claudio himself. He also founded Sebigas, a company with a portfolio of over 80 plants, specializing in designing, constructing, and managing biogas plants worldwide. He's the founder of Hidroelectrica Cavallo. This company built a hydroelectric power plant that holds the record for drilling the longest tunnel of its kind. So basically, Claudio's been working on making energy service and clean energy production work around the clock. And Energy Dome is really just sort of a logical extension of his career so far. So let's get into it.
Awesome.
Hope you enjoy the episode. first talked about doing this, I immediately was like, oh, we're going to spend this whole time talking about childhood and where we grew up and what we were using to become engineers eventually in life. But I thought it would be interesting to kind of start a little more recent, which is how we met. Because I think we met at COP28 this year, and where we met at the Museum of the Future, having cocktails with an AI robot. And yeah, I don't think we talked to the robot though very much. We were talking about what my main takeaway from COP28 this year was. I would tell people about what I was working on, or what we were working on at Aston, and how we were trying to, deploy these microgrids, or we'll call them private grids, that ran on 100% clean energy. And depending on who I was talking to, I would get somebody who would say, well, that's not going to work with clean energy, because clean energy isn't going to work around the clock. So we're going to have to use gas no matter what. And then I would meet with other people who would say, well, we just need storage. We just need to make sure that we have a solution. So that's where I wanted to start, because I think when I talk in my own circles about what you're working on at Energy Dome, it's just the light bulb, no pun intended, goes off, and people are like, oh yeah, that's what's been missing. So can you just give a high level description of Energy Dome?
Yeah. Thank you for the question. Thank you for having me here.
Absolutely.
Fantastic.
Thank you.
I think that, Energy Dome has been incorporated, has been founded just to give an answer to that demand of around the clock renewable and dispatchable electricity. So Energy Dome has developed a system and a technology which is proprietary, which make it possible to deliver around the clock electricity, renewable, which is dispatchable. It's a thermodynamic cycle, it's a thermodynamic process. The beauty is that it uses only off-the-shelf component, which are already used in other industries like oil and gas. And that make the technology very attractive, because on top of being very efficient, 75% round trip efficiency, and very cost competitive, the capex are 30-40% less than lithium-ion batteries. It is also available today. It is implementable today. We are not a lab company. We are not making any research on new chemistry, which may be available in 10 years or so, but we have developed a solution which we have been able to execute and to put on ground in a very short period of time, and we are ready to build in the market. So that is the beauty, and that, I think, is a real answer to the need of around-the-clock dispatchable renewables that we feel is really growing this demand all around, in every country and just in every corner around the world.
Yeah, it's funny. I just had a conversation last week. I asked somebody, I said, have you heard of Energy Dome? And they just, like somebody who had been in renewable development for a long time in the States. And they're like, oh yes, I read this article in the New York Times, which I saw that was a great piece that came out. So let me step a little bit further back. I'm kind of going to go very quickly backwards, and then we'll come back again to talk about Energy Dome and how you're deploying that. This isn't your first time thinking about around the clock clean energy, though. Prior to Energy Dome, you were working in geothermal. What inspired you to go from a technology which a lot of people, if we're talking about base load clean energy, geothermal seems like a full solution. So what are the challenges of geothermal that you saw as we need to find a better way, we need to find a different way and go into Energy Dome? So if you can just kind of talk a little bit about the challenges of of geothermal as around the clock baseload power, and and then maybe move into how Energy Dome is kind of solving some of those challenges of geothermal.
Yeah. The geothermal is very fascinating. I'm so happy that I spent, let's say, 8 years of my career in that sector, and is potentially a round-the-clock source of electricity, which is also quite well distributed, not equally distributed around the world, but quite well distributed. When I started Exergy, my previous company in geothermal, I think that we did great advantages on all the downstream technologies. On the binary cycle, we have been able to innovate, and we gave a strong impulse in that market. But then in beginning, I think 2013, 2014, the drop in price of solar PV became really a huge obstacle for deploying in geothermal. But the real obstacle of geothermal, in my view, are financial. So the geological risk, which is intrinsically associated to geothermal, is something that is priced very, very expensive from any, let's say, investor or lender. So the cost of capital associated to geothermal is really something which is really damaging, or let's say reducing very much the redditivity of all the geothermal investment. So in my view, the geological risk, which can be a risk of losing money by drilling a well, for example, which is dry, or just by delaying a project by 1 or 2 years or even more, is really unattractive to financial investor or infra fund that want to invest into that. Could be appropriated as an investment to oil major, which they know what does it mean. They have a balance sheet which is huge, which is big enough to finance that exploration activities with their balance sheet. But in my opinion, that is a kind of business which is available only for large corporate oil major that can really make decision to go there, to drop money from their balance sheet. That is the only way to make the difference. Otherwise, just the cost of capital will make geothermal not attractive against other source of energy. On top of that, there is a kind of intrinsic impossibility to standardize, because you never know what you find down there. So the temperature is different every location. The brine that you find is different every location. So standardization is an issue, and the lack of standardization means higher prices and less competitivity. That is one of the reasons why, at a certain point in time, when I saw that photovoltaic dropped, and I started to wonder myself if there was some possibility or some potential technology to be paired with solar PV, wind, to make solar plus storage or wind plus storage competitive against geothermal or against other, let's say, round-the-clock dispatchable renewables. And I got the feeling that there was that possibility, and that is the reason why I started to think in energy storage.
And so let's go to the beginning of Energy Dome. So you're thinking about this, which I do want to get into compressed air, compressed CO2, because compressed air has been a thing for a long time. Like, many people have said, oh, we can use compressed air. But the issue, and you told me this the first time we met, the issue with compressed air is the temperatures that you have to get to. And so you're leaving geothermal, you're thinking about getting into energy storage. And what is that process? A big thing on this show, we like to talk about that entrepreneurial journey, because obviously when we're pitching investors, we get about this much time to talk about the origin story. So we say, I was sitting there and I came up with this idea for Energy Dome, and then It happened. But take us back to that moment, and you can maybe drag it out a little bit longer than that. How did you arrive on the idea of compressed CO2 as that solution? When I heard it, it was like, I kind of had this moment where I was like, well, duh. That seems like a logical way to solve the issues of compressed air. So how did you go from, I want to get into storage, to landing on CO2 as the solution, compressed CO2?
Yeah, very happy about this question because this is very good. So after I started to think about the possibility of a new technology which could be competitive as solar in the energy storage field, I started to learn. I just started, let's say, to study. I just started to inform myself about all the potential available technology. So I studied quite deep compressed air energy storage, liquid air energy storage, and flow batteries, all the other gravitational and many, many, many other. But because I think that any innovation process starts from deep knowledge. So you can be able to innovate in a sector only if you know that sector more deeply and more in detail than many other. And that is that phase, which is the analysis phase. Is that phase where you use your left part of your brain. That is very analytical, very informational, studying. That is something like this. Then, the idea, when it come in a while. Because that is just a process to put together and make the synthesis of all the information that you have in your brain in the right way and take a conclusion. So I had all the ingredients in my brain, which was I have a deep knowledge of CO2 and thermodynamic behavior of CO2. For example, one of the reasons that CO2 is the best for storing energy is the fact that CO2 liquefy at ambient temperature under pressure. And that is the reason why we use CO2 in fire extinguisher. And we don't use nitrogen in fire extinguisher. Otherwise, for the same kilogram of gas, we should use a bottle, a pressure vessel, which is 10 times bigger for the same kilogram of gas. But after all those studying and putting together with my previous experience, I also had another company I founded in 2008, which was involved in biogas. And in biogas, we built more than 80 biogas plants, and we used a lot of double membrane gas holder to store the biogas produced before to burn this into engines. So when I got the idea to use the CO2 and using the nice property of CO2 to become liquid at ambient temperature, I immediately recognized the possibility to store CO2 at constant pressure and at ambient pressure in a large double membrane gas holder, which we call the dome. Mm-hmm. That was the missing piece to make liquefied or compressed CO2 attractive. So when I got this idea, it was just while on my trip back from Zurich, back home, I remember. So I was really on my itinerary, and when I came home, I just started to make a calculation like a crazy to get confirmation of the idea, because when you get an idea, the most important strategy, in my opinion, is to try to destroy it as much as you can in order to verify if that is reliable enough to survive and to be a good idea. So that is what I did. To me, any innovation, any real innovation process starts from a deep knowledge and a deep attitude in challenging the status quo. Always to be 100% convinced that you can do it better. There are solutions that you can improve, but you can improve by an order of magnitude. That is my attitude, and I always believe that it is possible to do things better. And I feel that that is the process which gave me the possibility to, at the end, to get this idea.
That's great. I love that concept of learning the numbers to leave the numbers. You have to learn all of the information so that it can become art, so that you can then actually get an idea out of the synthesis of all of that. I love that. I think the journey to something elegant, because when you look at the Energy Dome solution, it really is, as you say, standardized, repeatable, using off-the-shelf parts. It checks all of those boxes, all of those things that anyone has said about the challenges or why we won't be able to scale clean energy. I think that all of those components kind of are checked by the Energy Dome solution. But I do want to touch on one other point of Energy Dome, which I find fascinating, which is when you think about storage, you think of the sun is shining, we don't need all of that power, so we store it and then we use it at night. But with Energy Dome, it's slightly different. We don't just have to use it at night. How long can you keep it in storage before you actually have to use it? Can we shift it seasonally? Can we shift it weekly?
Since our process is a thermodynamic process which uses pressure and temperature, so the pressure part of the storage, it can be there indefinitely for a very, very long period of time. Then inside the process, we also have a thermal energy storage, which is the part that can degrade. And as a whole, the process, the CO2 battery, is able to keep and store electricity very efficiently, 75% round trip efficiency for daily storage. So if I charge today and I discharge tomorrow. If we go longer, let's say on a weekly basis, we can still keep a round trip efficiency, which is very, very similar to the original one. For seasonal too, but the point is that is the economical efficiency, which is not that high if you use the CO2 battery for a seasonal storage. So, because the return on the investment is based on how many charge and discharge per year you are able to do. So if you charge and discharge daily, obviously you pay back the investment much faster.
Greg, I have a basic question to ask real quick.
Yeah.
As I'm trying to wrap my head around different types of batteries, we've got like hydro batteries where the energy is stored in the water behind a dam. We've got lithium ion batteries where it's stored in the chemicals of the battery. And now we've got what I understand to be sort of like a CO2 battery, is how I'm starting to understand Energy Dome. To create the energy in the CO2, the potential energy that can then be released later, what is that process like? Do you need solar power or some kind of power from somewhere else to transform the CO2, or is it just...
Yeah, that's a good question. So what we do in our CO2 battery process is that we store the CO2 at ambient temperature and pressure in a balloon, in a dome, which is a double membrane gas holder, which keep the CO2 at ambient temperature and pressure. When we need to store the electricity, we just feed with electricity an electrical motor, which drive a compressor, and the compressor compress the CO2 from ambient pressure to medium pressure, high pressure, which is about 60 bar. And then after compression, that CO2 is under pressure, but is also quite hot, because by compression, the CO2 is warmed up. So we cool down the CO2 and we store that heat in a thermal energy storage. And then we condensate the CO2, which can be stored in very small or relatively small vessel, like a big extinguisher, like big fire extinguisher. Mm-hmm. In that process, so we use electricity to compress and liquefy the CO2. So at the end of the day, when sun set, we have all the CO2 which has been transferred from ambient pressure in the balloon into high pressure into the big fire extinguisher bottle. When we need the electricity back to the grid, what we do is just vice versa, the same process in the other way around. So we take the liquefied CO2 back from the bottle, we evaporate, we warm it up to the high temperature, like 400 degrees C, through the heat which we stored in the thermal energy storage, and then we inject the high temperature, high pressure CO2 into an expander which drives a generator which generates the electricity which is fed back to the grid. And finally, that expander exhausts the CO2 at ambient pressure into the balloon, into the gas holder, and that closes the loop. So it is a fully closed cycle. We charge the CO2 just at the beginning. We don't use and we don't leak any CO2 to the atmosphere. It's just a thermodynamic battery. So the process is a thermodynamic process, and that is able to store very efficiently and in a clean way all the electricity which is abundant when daylight, when sunshine, and which we need to inject back to the grid when sunset.
How do you bring the CO2 to the site?
CO2 is available. Today is available on the technical gas market, and CO2 will be more and more available in the future because it's a commodity which is going to be more and more available around the world. CO2 is necessary to produce all the synthetic fuels, starting from hydrogen. CO2 is coming from carbon capture and sequestration. It's coming from renewable sources. It's coming from direct air capture. We will decide, from where we can buy, but we just need a very small amount of CO2 because we charge the system only once to the entire life of the plant.
Goes back and forth.
Yeah, it's just back and forth, but remain exactly into the same system.
And so lithium-ion batteries they also have a relatively short life cycle. What's the life of an energy dome, of a CO2 battery?
That is a nice question. This is one of our beauty because we say that we can last for 30 plus years. So we have just steel components. We don't have any kind of rare metal, but we use only steel, and the pressure are quite moderate. So we are not going to extreme high pressure, and also the temperature are not extreme. So we stay normally below 400 degrees C, and that is something that make all the components also according to the, let's say, most used international rules. There are no limitation in hour that you can use that system. So we will not have any kind of degradation of efficiency. We will not have any kind of degradation of capacity because lithium-ion batteries degrade both ways. They degrade in efficiency, but they also degrade in capacity. We don't have that, so we can keep all the original performances for 30 plus years. And that is really a beauty that is one of the advantages that we have, together with the fact that we don't use any kind of rare metal in a world which is going to be a bit less globalized than was before. This is a big advantage, not only in terms of energy efficiency, but also in terms of energy security and energy reliance. We know that those are very important arguments that are under discussion at very, very high level all around the world.
Yeah. Yeah, I thought that was amazing when I heard that. I mean, I think there's so many of these objections that, unfortunately, as we think about energy transition, there are different groups want to keep their business in business and different countries want to keep their commodities in business. And so it's easy to find these issues with storage or these issues with different types of technology. And luckily you beat yourself up enough when you were starting the company to find all of these challenges that someone might say, yeah, that's not going to work. That's not going to work. But I do want to ask that question, which is, since you said as an engineer or an entrepreneur is like, try to destroy your idea. Is there anything that you came to where as you were trying to destroy the Energy Dome idea, is there anything that you said, I could destroy the idea with this fact, but I'm going to go forward anyway? Was there anything left on the checklist that you said, this is a limitation, but it's not a big enough limitation for me to kill the idea?
I think that one of the most important thing that you have to realize is that you need to be honest. If you really try to destroy the idea, if you really think something, if you really find something which is not working, you have to be very straight and honest and accept it. So by doing a very strong stress test on the technology, me and together then with the founding team, and also in the future, in the next 4 years, we have continued to do that. The only thing that we found is not really, let's say, a deal breaker at all, but it's just a disadvantage. Obviously, we need a bit more space than lithium-ion batteries need. And very honestly, thinking about that, so we said, okay, we need maybe 5 times the space if compared to lithium-ion batteries. So that is a disadvantage. But very, very honestly, thinking about that, since we are talking about energy transition, and energy transition is pretty much about solar production, wind production, and that. So we made some evaluation because at the end, calculation and number matter in this. So we said, okay, let's try to quantify. Let's try to quantify how this disadvantage can be important. And what we found is that the use of land, if compared to solar photovoltaic, is just a fraction. So if we consider the area that we need to produce a certain amount of energy that we store in one day, the land that we need is around 7% of the land of the solar photovoltaic. But on top of that, we have also identified a solution to convert that disadvantage into a strength. Mm-hmm. Because we use that land for the dome, which is the most land-consuming component that we have in our CO2 battery. But the dome can be covered with a photovoltaic panel. So if now that we have also developed that solution, we have not discovered there is a special shape that we have developed, but with this solution, we can also avoid this kind of disadvantage. And in that case, if we put solar PV on top of the dome, at the end, we are even more compact than lithium-ion batteries. Yeah. So it takes a bit of time. Obviously, the important point at the beginning was to prove to ourselves that there were no bottleneck. But if the only disadvantage is the land usage, now we have a solution also to improve that parameter and to be even more, let's say, attractive and competitive than lithium-ion batteries. The only real limitation today, finally, is that maybe we are not the ideal solution to be installed in the center of a city, where you really have no space. In that, or where because in that case you cannot install, but there are 90+% of the potential installation which normally we received inquiry for that are always with enough land and space available to install our technology.
I'm just thinking about how, as you were talking about standardization across locations for geothermal, the challenge with geothermal is that it's hard to know what's underneath the ground in each place that you go. So you may end up with something coming up that is either, as you said, really a dry well, or just geological issues. What is under there? Is there some sort of thing you didn't know that was going to come up that's going to kill the whole entire project? Are there any of those things with Energy Dome? I'm just imagining like altitude or something, like just in terms of atmospheric pressure. How big of a challenge is that? I mean, it seems pretty understandable, but are there any other things that you have to consider in each location? I know space is a thing. Height is probably a thing that you have to think about, but are there any other of those pieces that are challenging for scale?
Thank you very much for this question. I can really put the accent on one other, let's say, beauty of our process, which is to be totally temperature independent. So our process, our CO2 battery can be installed fully standardized with exactly the same component, with exactly the same specification in Alaska in winter or in Texas in summer or in the Middle East. So we can work at 100F, 120F, plus we can also go below zero without any problem and exactly with the same performances. 0 point something percent, but really, the performances are not affected by that. We have, just in case of very, very high altitude, there are a few locations around the world where altitude goes really very, very high. There are some geothermal plants coming from geothermal, which are located at 4,000 meters or 5,000 meters, which is, let's say, 15,000 feet above sea level in Chile. But those locations are very remote because there is the geothermal resource. But you will never go to install there a gas turbine power plant, which, by the way, would also be, let's say, downrated. So in our case, I can say that till to 6,000 feet, we can almost work without any kind of, let's say, downrating. If you go above, you just, with the same gas holder, with the same balloon, and with the same plant, you will just be able to store a certain percentage of kilowatt hour less. So it is just a problem of rating. So high altitude, you have to derate a bit the nominal value of the battery, but the battery works without any problem and with a slightly, let's say, even higher efficiency, because the pressure ratio of the compressor and the pressure ratio of the turbine increase. So there is a slightly improve in round trip efficiency, but there is also a slightly, let's say, reduction of capacity. But that is nominal, it can be calculated upfront, and that can be put in the economical calculation to see if there is the return.
How many megawatts can you, of a size? Is there a standard size, or is it scalable? I mean, from a standardization standpoint, it sounds like you're trying to get this as repeatable as you can possibly make it. Are you aiming for one specific size, or will you change the scale?
Yeah, it's we have developed a standardized solution, which is 20 megawatt, 200 megawatt hour. In reality, compressor, during charging is 24 megawatt. During discharging can be 18 or 22, depending, from different configuration. And this is the minimum size of the battery. So the only limitation that we have today is that we have defined a minimum size of the CO2 battery. We are not bidding for 10 megawatt. We are not bidding for 5 megawatt. And that is related to the fact that the compressor and turbine really achieve almost the best efficiency at that scale, at that size. Upwards, we have no big limitation because we can combine those modules and we can aggregate those modules in different configuration. We can put 20 compressor and 10 expander, and we can build, a giga scale, a 1.5 gigawatt hour CO2 battery, based always on the exactly same component, which are standardized, which do not introduce any additional risk and get access to very low cost of capital, being standardized.
Sure.
That is the concept that we have in terms of business model. And I think that is really, it makes sense because, we have to pair the standardized solar photovoltaic panel or wind turbine, which we work together with.
Yeah, you've mentioned this several times, and it's so funny coming from a mechanical engineering background to have to think so much about finance. You've mentioned about the financeability of what you're doing, but at the beginning of this year on this podcast, we talked about kind of the primary challenges in deploying clean energy, and one of the biggest ones that comes up is finance. It seems like all these government programs, all these special tariffs, all these investment tax credits, everything is about lowering the cost of capital and making it easier to get it financed and easier to get it deployed. And I just read a great book, and I'm blanking on the name of it, but it was about what makes large mega projects like energy projects or large construction projects go over budget. And it's always standardization, modularity. If you have modularity, things don't run over budget. If you are trying to make specialized projects, things run over budget. And you mentioned that about geothermal. It's different everywhere you go. It was so fascinating to me is just this idea that you can have something that in a lot of ways is traditional. You're using a lot of the same physics that you would use in turning a turbine, all of those pieces, all of these kind of gas cycle processes, but you're almost making this like cookie cutter. It's fascinating to me. You're making this sort of standardized thing that could almost ship in the kit and then be installed several times over. So,
if I may, sometimes I'm joking, in the company, and I'm saying that Energy Dome will fully succeed when we will have very, very few engineers in the company, and that will means that the product will be fully developed at that point in time, and we will not need any additional modification. This will bring a lot of comfort to investors and financial institutions that will be really ready to develop large capital with very low cost. And at the end, we will succeed only and only if we will create a big impact in this market. And that is the way to go. It's not tailor-made. I spent a lot of time in geothermal trying to turn around the issue of having every time a different source. But there you have no solution. In this case, we only have a grid connection. Fortunately, let's say the grid frequencies are standardized. Okay, we can have 50 cycle in Europe or 60 cycle in the US, but aside that change, everything can be standard. And the other big beauty of CO2 battery is that we are totally temperature independent. So we can really produce a product which can be deployed everywhere with standard specification.
I thought it would be fun to show you guys. I tried to make a diagram of I don't think I got it right, but it was dome, heat, cool, store, then heat, use, cool, store, right?
Yeah.
amazing.
Right.
I think as a total outsider, I mean, I didn't know much about this technology before we spoke, so it's exciting to hear about a totally new way of thinking about energy storage that's self-contained, and just brilliant. Honestly, I think it's really brilliant. So.
Yeah. Now I'm going to go back, way back. You talked about starting a company in 2007, I think is what you said. I'm very curious. Anytime I hear somebody who's spent their life as an entrepreneur, it's not all glory all the time being an entrepreneur. So it takes, usually it seems like something happened or some kind of inspiration happened as a kid. So I'm very curious, was there something as a child that you were either exposed to, your parents gave you, maybe it's somewhere you grew up, that kind of sent you down this path? And
Yes, there has been something quite early in my life. I got the right stimulation, I think, from my parents. And I'm getting from a town in the north of Italy, which is very close to Swiss border on Lake Maggiore, which is very close to the Alps. And there, most of the first industries in Italy born there. Just because there was a lot of availability of water, and the town was connected with channels to Milan, but in Milan there was no electricity available. But there was electricity available because there were hydropower plant. The first hydropower plant had been built there. My town, which is small, has been the first town in Italy to have electrical public lighting around the town. Much before than Rome and much before than Milan. There, the first car in Italy has been built, and many other machineries. So I remember that my father told me about those stories, and I've been quite impressed about the fact that there have been, let's say, people able to be pioneer into some industry which is still very relevant. Okay, now we don't build any more, let's say, cars in my town because the electricity is in other, let's say, location. But I think that learning gave me the courage to be able to be an entrepreneur, to understand that also coming from a relatively small town, you can really do something big. Mm-hmm. That is the most important thing that I got. And that is something that I feel I bring inside me. What I learned from that is really that there are no limits. You can really think big. You can really think that you can start to make a revolution starting from a small town, which is not well known. And I think that is very important to be an entrepreneur because you need to be, let's say, straightforward. You need to think about a lot of things, but at the end of the story, you need to have the courage in front of the challenge that you have. So I think this is some of the best lesson I learned when I was a child. Mm.
So how about engineering? How did you go into that? Was that part of your curiosity from entrepreneurship and doing something big, or was there?
Yeah, I think that, when you are that age, any decision is not really rational, You have to take a decision, but you don't know what you are going to do. Right. I had classical studies at the gymnasium before my university. I had not in mind to be an engineer. In the last period before to finish my high school, I got some more interest for some technical stuff, let's say a race car. And I said, okay, I want to go there and I want to be, let's say, a designer of a race car. That's my dream. Then I started the university, but then during the studies, I lost this passion for race car and Ferrari, which I still keep, in terms of supporter. Sure. By the way, yesterday Ferrari won, so that's great. But not let's say that much to try to spend, let's say, my career designing race car. A professor which I met at the university really inspired me, And he was professor of energy system and energy machinery. And at the end, you need people that inspire you.
Yeah.
And the reason why now I'm spending all my career in energy, today in energy transition, but also 20 years ago in energy production, is because my professor inspired me.
That's awesome. Yeah, I tell that story sometimes about, I actually went to college because I had played music my whole life and I wanted to build recording studios. And so I asked somebody, well, if I want to build recording studios, what do I major in? And somebody said acoustics. And so I went and I said, well, where's the acoustics department? And they said, well, it's physics. And so then I went into physics. And then I learned about recording studios, and I found out that what matters a lot is power quality. You had to get the power service right in the building to make your audio sound good. And so then I just took all these power courses, and now here I am designing power quality. Now, 15, it's so funny. Even you mentioned race cars. I mean, combustion engines and all of those things, it's the main component of that, making those efficient. I love hearing these stories because it almost seems like when you look back, maybe it's because we're so good at storytelling as people, but as you look back, it's almost like it's not even an accident, all the way back to the passion for race cars, or all the way into this, and yeah, there's people along the way that inspire us to make that slight turn that it's like, well, you could still work kind of near it and you can still root for Ferrari. And do have one last question for you, which is, if you could stand on stage at COP28, these people standing in the audience trying to figure out how we're going to get rid of fossil fuels or stop using fossil fuels, what would you say to those? What would you say to the crowd?
I'm a very positive guy, and I can just transfer to the audience what I really feel. And what I really feel is that if we believe, we do it. We can really find a way. But the only important point is that we have to believe and we have to work strong, and there are all the conditions to succeed. We can be one part, and we aim to be a piece in this big puzzle, but we need strong people, strong team, which are laser focused on the target. Put those guys in the condition to operate, and they will solve the problem.
Amazing. Thanks for spending the time with us, Claudio.
It was great to be with you.
Yeah, great to be with you.
Thank you. I learned so much. I'm really excited.
Thank you.
Hey, it's Flo. We would love to hear from you. What questions do you have about the future of electricity and power? What guests do you want us to interview? You can let us know and help us get the word out by commenting, rating, and reviewing us on Apple Podcasts or Spotify. You can also join the conversation on Twitter and Instagram. Our handle for both is @the WC Podcast.
Thanks for tuning into this episode of the World Changing Podcast. Be sure to follow us wherever you get your podcasts, iTunes, Spotify, YouTube, to hear the latest episodes.